Quantum computing is a beautiful fusion of quantum physics, computer science, and information theory, a powerful synergy pushing the boundaries of what's possible. Imagine a world where cybersecurity is impenetrable, data analytics and artificial intelligence reach new heights, complex optimizations and simulations become effortless, and searching vast datasets is instantaneous. These are just glimpses into the transformative potential of quantum computing. In quantum computing, the basic unit or building blocks of information is the qubit or quantum bit. Just like the bits in the laptop or phone you're watching this video on, qubits form the foundation of quantum data. But unlike classical bits, which can only be a 0 or a 1, qubits can exist in multiple states at once. This unique property allows quantum computers to perform complex calculations at unprecedented speeds, pushing the boundaries of what traditional computing can achieve. Quantum computing can feel overwhelming, but together we'll break it down step by step. Let's start with the basics. In classical computing, like in your laptop or smartphone, a bit is the smallest unit of data, either a 0 or a 1. Think of it like a light switch, either on or off. But in quantum computing, we have qubits, which are, let's say, a little more flexible. Now imagine a spinning coin. Before you stop it and look, it's both heads and tails at the same time. This is a bit like a qubit. Thanks to a strange quantum property called superposition, a qubit can be in multiple states at once, holding both 0 and 1. This unique ability gives quantum computers the power to handle complex calculations in ways that classical computers can't. So what makes qubits quantum? To understand quantum computing, we need to look at 4 special principles from quantum mechanics: superposition, entanglement, decoherence, and interference. First, there's superposition. Imagine a tiny particle that isn't just in one place or state, but can represent multiple possibilities at once. Imagine your friend is skating at the park, moving so fast that it looks like he's at both edges of the skate ramp at the same time. He's not just here or there, he seems to be in both places at once, but then you take a photograph and in the picture he only appears at one edge. That's how superposition works. In quantum terms, particles like qubits can exist in multiple states at once, like being at both edges. But when we measure or observe them, just like taking that photo, they settle into just one specific state. Then we have entanglement. When 2 particles are entangled, they're linked together, even when far apart. So if you know the state of one, you instantly know the state of the other. Next is decoherence. This is when quantum particles, like our qubits, lose their quantumness over time, collapsing into a single classical state we can measure, kind of like the coin finally landing on heads or tails. And finally, interference. Interference happens when these quantum states interact with each other, boosting certain outcomes and lowering others, like pushing the qubit system probability so that the correct answer is more likely and the incorrect answer is less likely. Together, these principles make quantum computing powerful, giving qubits the ability to explore complex problems in ways regular computers can't.
Quantum processors don't solve problems the same way regular computers do. While a classical computer has to go through each step one by one, a quantum processor can explore many possibilities at once. Imagine trying to find the fastest route through a maze. A classical computer would test each path individually, but a quantum processor can explore multiple paths at the same time, finding the best route much faster. This ability to process multiple options simultaneously makes quantum computing incredibly powerful for solving complex problems. Quantum computers hold amazing potential, but don't toss out your laptop or tablet just yet. Quantum computers still have some big issues that keep them from being ready for everyday use. First up, decoherence. Even a tiny temperature change or a bit of light can mess them up, causing something called decoherence. So they need a perfectly controlled environment to stay focused. Then there's error correction. Quantum error correction is much more complex than classical error correction. Traditional error correction techniques rely on copying information, but quantum mechanics prohibits the exact copying of quantum states. Scalability, a nightmare. Adding more qubits makes things way harder to control. And don't forget noise. Environmental factors like electromagnetic interference throw qubits off their game. So, while quantum computers are incredible, they're still a work in progress. Stick with your laptop for now, but keep an eye out. Quantum computing is full of potential.